Julien Benoit, thanks so much for coming on to Evolutionsoup all the way from your office in South Africa. You are a senior researcher in therapsid paleontology based at the Evolutionary Studies Institute, University of Witwatersrand, currently researching pre-mammalian evolution and the fascinating link between reptiles and mammals. Welcome to the show, Julien. You originate from France and now you work in South Africa. It must be very different from where you grew up. So are there any French speakers that you can hang out with in Wits University?
Hi, Mark. Thank you for having me on the show. So yes, actually, you would be surprised how many French researchers are working in South Africa. Mostly archaeologists, actually, not so much paleontologists. But I have a lot of archaeologists among my colleagues, and so there's a lot of us. It's kind of they call it a French invasion sometimes.
Before we dive into the origin of mammals, let's just hear a little bit about your background. Julien, were you always interested in ancient life, and can you describe the path that led you to where you are now?
Well, when I was a child, of course, I'm part of that Jurassic Park generation that grew up with live dinosaurs in the cinemas, very realistic dinosaurs in cinemas. Mm-hmm. And it's funny to look at the statistics, like you see the number of paleontologists suddenly bumping right after the movie came out in theaters. So I'm kind of part of that generation. Although my interest in really becoming a paleontologist came quite late in high school, and I used to go. Well, when I was a child, I used to go look for fossils with my grandfather, but that was just a hobby, not really a vocation. But yeah, when I was in high school, then I decided I wanted to make this my job, and so I had a license in science, a BSc for English-speaking people. So I had a BSc in science, and then a master's. I moved to Montpellier to get a master's in paleontology, and then I did my PhD in Montpellier on African mammals. So at that time, I just focused on mammals, on fossil mammals from the Cenozoic, and then when I got my PhD, I was offered a postdoc in South Africa to work on things that are even older than mammals. So they heard of what I was doing with my mammals and wanted me to apply that on older stuffs. And they just acquired a CT scanner, and I happen to be I'm not calling myself an expert, but I work a lot with CT data, so X-rays, the study of fossils using X-rays. So because I was doing this, they wanted me to apply that on their fossils in South Africa. So South Africa has that huge fossil record of early pre-mammalian animals, and they were curious to know what kind of stuff I could find. And so I moved to South Africa as a postdoc, so postdoctoral researcher, which is kind of a temporary job, a temporary contract as a researcher, and that temporary contract turned into a permanent position in 2018.
Right. Let's get into the origin of mammals. First off, why do we think that mammals are descended from reptiles? What is the modern evidence?
So in modern mammals, you have quite a diversity of modern mammals today, but they can be categorized in three big groups. So the group that we belong to is the placental mammals that reproduce with a placenta. There are the marsupial mammals that have a pouch, and there are the monotremes, so the platypus and the echidna, which in their particular case reproduce by laying eggs. So they are kind of between two worlds, between reptiles and mammals, because just like mammals, they have hairs and they milk their young, but like reptiles, they don't have nipples. They actually the secretion of milk is made through the skin directly. There's no particular area dedicated to milk secretion on their belly, and also they lay eggs, which really makes them like very reptilian in their reproduction biology. Also, when you look at their anatomy, platypus in particular are extremely strange in terms of their anatomy, but their anatomy is also interesting because when you look at the shoulder girdle, their shoulder girdle has a bone called the interclavicle. So you have your two clavicles here.
Yeah.
And there is an extra bone in between. That's not the sternum. It's an extra bone that connects the two clavicles. It's called the interclavicle, and that's also extremely reptilian. If you know reptilian anatomy, you're like, what's that doing here, basically? So just looking at modern mammals, that's where the idea that mammals are just a funny kind of reptiles came from originally. Also, now we have DNA, and thanks to DNA, we know that mammals are very closely related to reptiles in a group that we call the amniotes.
The animals we are going to be focusing on today are the synapsids, a group some refer to as mammal-like reptiles. As we'll see, synapsids have been around for a very long time, leading right up to today. It all began, however, way back in the Permian, about 300 million years ago. Isn't that right?
So the lineage that mammals belong to is called the synapsid, after a hole that's on the side of the skull. We will talk again about that later. But yeah, it's called the synapsid because of that. And that particular morphology, the hole on the side of the skull, we can trace it back all the way to the Carboniferous, actually. So even older than the Permian, we are talking about 320 million years ago. And the earliest synapsid already had that particular morphology. But in general, in the overall anatomy, and that's what's very interesting, it actually confirms the prediction that we could make on monotrim, that the ancestor of mammals would be more reptile-like than mammal-like, is that they were very reptilian with a very long tail, scaly skin. We have very beautiful fossil of the scaly impressions on the skin of many of our early synapsids in Germany, for example. There are very nice examples. And they were sprawling. So it means that instead of having their legs straight under their body, like if you look at your domestic dog or cat and you're facing them, you will see their legs are straight under their body. That's a mammalian feature that we also find in dinosaurs, but it's called convergent evolution. It's a parallel evolution. But all those early reptiles, including from the Carboniferous, including our ancestors, the synapsid, they were all sprawling animals, which means that their legs were on the side of their body and they were moving sideways like this. And this is confirmed by footprints also. We have a lot of trackways of those animals in France, in Poland, for example, in Britain also, I think you have some of those. And so that's, these early synapsids, what they have in common with mammals, so these are quite conspicuous features of their skull. So the first thing is the hole on the side of the skull. So that hole is called the temporal fenestra. So temporal because it's on your temp here, and you can feel, you can guess what it's for if you move your lower jaw, and you put your fingers on the side of your head, and you will feel a muscle moving here. It's a muscle that goes from there to the lower jaw, and it's called the temporal muscle. Hence the name, the temporal fenestra. So that hole in the skull is very typical of the synapsids. And you can still see it today in mammals. So I got my tiny mammal skull. So here on the mammal skull, you will see here you have the orbit, so the eye socket. And here on that side, that's your temporal fenestra. And you see it really makes a hole in the skull like that.
Yeah.
So, and it's the same in humans. So in humans, that temporal fenestra is actually right behind your cheek here. So you have your cheekbone, and you can feel the muscle going under your cheekbone all the way to your lower jaw. That's your temporal fenestra. So that's the first thing we have in common with those reptiles. And the second thing we have in common with those reptiles is that our dentition, our teeth, are divided in three parts. You have a canine, and the canine splits your dentition between the pre-canine dentition, your incisors, and your post-canine dentition, so your cheek teeth. And that's something you will see also in the earliest synapsids. The most famous is Dimetrodon. So Dimetrodon with the sailed back is the most famous synapsid, and it's extremely reptilian looking in every aspect. But when you look at the skull, you see that temporal fenestra and that division of the dentition between post-canine and pre-canine dentition. And the
so a bit like our teeth.
Exactly, and that's still something we do have today. So this is directly inherited, from these early reptilian-looking ancestors. So that's the very root of the mammalian family tree. It's among those Carboniferous reptilian-looking animals that had these two particular features. And these early representatives, so now the synapsid family tree can be divided in four big parts. So the earliest part of the family tree, so the main trunk of the tree, would be the pelycosaurs. So the most famous pelycosaur is Dimetrodon, as I already said. So the pelycosaurs are the most reptilian-looking animals. The body was low on the ground, sprawling posture, like very reptilian-looking way of moving, long tail, and scaly skin. We have good evidence of that scaly skin. Then when you move up, so that's in the Carboniferous and the early Permian, so about 320 to 300 million years ago. Then you move up to the Permian, particularly the middle and upper Permian and the Triassic, and you have the therapsids. So therapsids are the next stage in the evolution of mammals, and they differ from pelycosaurs again in the temporal fenestra. The temporal fenestra becomes very big, actually, bigger than the orbit. And so that's still something you see in mammals today. You see the temporal fenestra here is a lot bigger than the orbit. So this is something we inherited from those therapsids ancestors. And in terms of body, their posture would be what we call semi-erect. So instead of having the legs on the sides like this, the legs would be slightly erect. So very much like a crocodile when a crocodile walks. When it's on the ground, you see when you look at a crocodile, when it's resting on the ground, it's in a sprawling posture, but when they move, they make a push-up. Yeah, exactly. They stand up a bit. Yeah. So that half push-up posture was typical of therapsids. And the therapsids themselves give birth to the cynodonts somewhere in the late Permian, or at least for now, the earliest cynodonts fossil are late Permian. So it happens very quickly, as you can see. You reach the early Permian, you lose the pelycosaurs, and they turn immediately into therapsids and cynodonts. So the next stage is the cynodonts, so which means dog teeth. And these dog teeth are very special because they are the cheek teeth. And these cheek teeth are a little complex. They have 3 cusps. They look like a clover. They have that clover shape outline, just like the incisors of a baby dog. If you've ever looked
yeah.
at the incisors of your dog, when it's not too old, when your dog is not too old and the incisors are not weared off, you will see that they have that clover shape. And so that's where they get their name of cynodonts. But it's not the incisors in cynodonts, it's the cheek teeth. And this means that cynodonts started doing something that we still do today. They chew. They chew their food. Reptiles don't chew their food. If you look at a tortoise, if you look at a crocodile, they tear chunk of whatever they're eating. So for your tortoise, it would be salad. And for your crocodile, it would be meat. And they swallow whole chunk. They literally munch everything. So they don't really chew their food. And because of that, they have no cheeks. So these fleshy bits that you have on the side of your mouth, these are innovations that you share with cynodonts. This is a derived feature shared by cynodonts and mammals. And this keeps the bolus inside your mouth when you are chewing. And these are made by an extra muscle called the masseter muscle, which is not very developed in reptiles. It's there, but it's small, and it has a minor importance in jaw movements. But in mammals, it becomes extremely important. And in cynodonts, it's already the case. So that's the cynodont level of evolution. And in cynodonts, the earliest cynodonts are still semi-erect, so still half push-ups posture. But then in derived cynodonts, the limbs will finally become fully erect, straight under the body. So, and we reach that point. The skeleton has turned from a reptilian skeleton into a mammal-like skeleton. At the end of the Triassic, we've reached the point where the skeleton is mammalian in most respect. I won't say every respect, but mammalian in most respect. And in the early Jurassic, very late of the Triassic and early Jurassic, as the dinosaurs are rising, cynodont size shrinks quite suddenly in the fossil record. Cynodont size shrinks. They become very, very tiny animals, shrew-sized animals, nocturnal, and they basically turn into mammals. So in the early Jurassic, we reach the point where we have proper mammals, stuff that we can call mammals. So the skull is very similar to that of a shrew. The dentition is now completely differentiated with we don't speak about precanines, but now we speak about incisors, canines, and then the post-canine teeth are turned into premolars and molars, just like modern mammals. And so all the mammalian history from that point on is derived from that shrew-like animal, like the elephants, from elephants to whale to humans to monkeys, sloths, all those weird stuff that exist today, they are all derived from that tiny nocturnal animal that was born in the dinosaur world in the Jurassic. So that's the 4 steps of synapsid evolution: pelycosaurs, therapsids, cynodonts, and finally mammals. And every time you lose a degree of reptilianness, if I may say.
Julien, when do we stop talking about mammal-like reptiles and start talking about just mammals?
Yes, so that's actually a tricky question. Actually, it's very difficult to decide when we stop talking about reptiles and when we start talking about mammals. So consensually, so usually researchers agree to call pelycosaurs, therapsids, and cynodonts, they agree to call them mammal-like reptiles. So the transition between the two would be sometimes between the cynodonts and the mammals. And this makes sense because we call them mammals, but this transition was very easy in the early days. Not the transition, but that split between mammal-like reptiles and mammals was very clear-cut in the early days of paleontology because we had very few fossils. But now we've documented with the transition from mammal-like reptiles all the way to mammals with such a high degree of accuracy that it has become extremely difficult to draw a clear line between what is the last mammal-like reptile and what is the earliest proper mammal. And at some point, it has been decided arbitrarily that there was just too many transitional species. So we had to draw that line arbitrarily to say, okay, that's the last cynodont, that's the earliest mammal, and in between, everything in between, there's nothing in between because otherwise everything is stuck in that line of intermediate species, because they change so gradually that it's very difficult to distinguish. So, and that line, that arbitrary line that we decided on, is the transformation of the lower jaw joint from a reptilian jaw joint into a mammalian jaw joint. So reptiles have a very complex lower jaw, and early synapsids also have that. They have many, many bones in their lower jaw, up to 8 bones, and mammals only have 1 bone. It's called the dentary. So if you look at the jaw of a mammal, you see there's no visible suture inside the lower jaw. It's like one solid piece of bone. That's not the case in reptiles. And what we see in the evolution of synapsids is like in pelycosaurs, you have the whole set of bones, and then in therapsids and in cynodonts, you see most of the bones becoming very, very tiny and moving at the back of the jaw, being replaced by the bone that's holding the teeth. So the bone that is holding the teeth becomes more and more important and pushes back the other bones at the back of the lower jaw. And what happened is that at some point, the jaw joint of the reptiles becomes so tiny. So the joint between the skull and the lower jaw that reptiles have becomes so tiny that it's just a thin rod of bone on the inside of the lower jaw. So that reptilian jaw articulation, that reptilian leftover, if I may say, makes an articulation between a bone called the articular and a bone on the skull called the quadrate. In mammals, there's no longer an articulation between the quadrate and the articular. You have an articulation between the dentary here and the squamosal here. So the two bones, it's like the two bones articulate like this.
Yeah.
And gives you the jaw articulation. So in mammals, you have the squamosal and the dentary, but in reptiles, you have the articular and the quadrate. And so you have, in cynodonts, you have that thin rod of bones that is the equivalent of the articular, and you have that big dentary that has now taken over all these reptilian bones. And it's bigger, and it begins articulating with the skull, forming the mammalian jaw joint. And what's very interesting is that in the most derived cynodonts, those at the verge of the transition between cynodonts and mammals, they have 2 types of jaw articulation. They have both the reptilian and the mammalian jaw articulation. So that's very interesting. It's like it's like the very transition between the two. And so how do you decide what's more mammalian, what's more reptilian if you have the 2 conditions at the same time? Well, they just say when the squamosal dentary articulation is bigger than the quadrate articular articulation, you have a mammal. And if the quadrate articular articulation is bigger, you have a reptile. So quadrate articular bigger is a reptile, and squamosal dentary articulation, you have a mammal. So you just need to look at the size of the two parts of that jaw articulation, that transitional jaw articulation. So, and that was and what's interesting about that is that, in fact, the fossil record is so complete, is so well documented in that transition, that in fact you have a species that is right at the verge of the two. It's called Diarthrognathus, so which means the jaw with two articulation, Diarthrognathus. And the mammalian articulation is exactly the same size as the reptilian articulation in that guy. So it's right on the line. Even when we try to split the reptiles and the mammals with an absolutely arbitrary, completely man-defined line, even that the fossil record says no. you still have something that goes right on the line. Like it's exactly what people say when people say nature doesn't care about man-made boxes. That's exactly the situation. We made the two boxes, and yet there are still things that come and stand right on the edge between the two boxes. And so for the little story, this articulation, this reptilian articulation, is not completely gone in us modern mammals and even in modern humans. It has migrated into the middle ear to become the ossicular chain. So now the reptilian articulation helps us hearing, basically, enables hearing in modern mammals. But the articulation between our squamosal and our dentary is very big, and the articulation in our ossicular chain between the quadrate and the articular, which now we call the hammer and the anvil, is very, very small. So we still follow the definition that was given by paleontologists between mammals and reptiles.
So the jaw bones of these more reptilian animals became basically our modified inner ears, became our ears.
Yes, so they became the ossicular chain. So in the ossicular chain, you have the stapes, the anvil, and the hammer. The hammer is the articular, the anvil is the quadrate, and the stapes is the stirrup is the reptilian stapes. So this is still the reptilian jaw joint is still there, but now it's completely co-opted into a new function. It doesn't function as a jaw articulation anymore, but the articulation is still functional. It's still there. Our ossicular chain still is made of bones that articulate to each other, and it's the same bones as are in reptiles.
Wow, really fascinating. Okay, let's look at the indicators within these animals that link reptiles with mammals. When we think of reptiles, we think of cold-blooded creatures. So how could cold-blooded animals become warm-blooded ones?
Yes, so the transition from cold-blooded to warm-blooded, and to make it simple, we talk about ectothermy for cold-blooded and endothermy for warm-blooded, but just to make it simple, we'll say cold-blooded and warm-blooded. But there's a whole jargon behind that that I just want people to know that it exists, even though you don't have to know exactly the words that we use. But yeah, the transition from cold-blooded to warm-bloodedness is something that we believe happened during the evolution of synapsids to mammals, even though there was two very recent papers that actually say that all amniotes were originally ancestrally warm-blooded. A very bold claim, I may say, but they are putting together some evidence now for that. But for today, we will assume that that transition from cold-blooded to warm-blooded happened in the synapsid lineage. And it also happened somewhere in the dinosaur lineage that led to the birds. So it's again another example of parallel evolution. And so warm-bloodedness is a very difficult character to trace because it doesn't leave any fossil record, or a very tenuous fossil record. It's a matter of soft tissues, and soft tissues, of course, and physiology, and soft tissue and physiology do not fossilize well. So we have to rely on indirect evidence to reconstruct that transition from cold-blooded to warm-blooded. So the earliest mammals, as I said, were nocturnals and very small. In most part, to avoid competition with the growing success of archosaurs. There are other factors, of course, probably climatic factors, but the big idea is that they were small and nocturnal. So unlike our modern lizards, there's very little chance that they could bask in the sun to warm their body. So usually it is accepted that the early mammals, so the fourth step in our history of synapsid evolution, they were endotherm, like warm-blooded. And once again, I have to cite another recent paper that says that actually they may not have been warm-blooded. But I just want to highlight the fact that what I'm talking about today has been contested in the last 2 weeks in two opposite ways. Like a team saying that the earliest mammals were not warm-blooded, and another team coming to the opposite conclusion that actually everybody was warm-blooded. So it's highly debated, highly debated. But the consensus for now is that we kind of all agree, most of us agree that mammals were warm-blooded. We kind of all agree that the pelycosaurs were probably cold-blooded because, as I said, they are reptilian in all their biology. They have scales, they have a sprawling posture, they have also, when you section the bones, you see a line of interruption, growth interruption, just like in a tree. When you cut a tree, you can count the growth lines. Yeah. So you see that also in those guys, and it's because they are warm-blooded, they stop growing in winter, or they grow more slowly in winter. So now the question is about therapsids and cynodonts, and there it's kind of difficult how to reconstruct that transition. So most therapsids, I'm not going to do that. Most therapsids we are usually considered cold-blooded, and we consider that the transition from cold blood to warm blood happens in cynodonts. But as I said, there are a lot of inconsistent evidence. If you look at the bones, if you cut the bones in therapsids, you will find that some therapsids do not have lines of interrupted growth, which would suggest they were warm-blooded. But when you look at some cynodonts, you will find those lines in some cynodonts. So maybe there were many occurrences actually of warm-bloodedness. When you look at the isotopes, so the chemistry of the bone itself, same thing. We find that most Triassic species, regardless if they are therapsids or cynodonts, show signs of warm-bloodedness, but not in the Permian. So again, we may be talking about more than one origin for warm-bloodedness in the therapsids and the cynodonts. And when we look at the anatomy, so usually in the anatomy there are indicators of warm-bloodedness. The loss of the pineal foramen, for instance, which is a hole on top of the skull for a third eye. So it's not nothing supernatural. It's that third eye is present in lizards, in the Komodo dragon, for example, in iguanas, in bearded dragons, if you have those animals in a terrarium at your place. you may have noticed a transparent scale on top of the skull. That transparent scale accommodates an eye called the third eye, and that eye tells your animal when it's night and when it's days, and so it tells your animal when to bask, basically. So there is a direct connection to the brain that says go basking, and that eye was there in all therapsids, the earliest cynodonts, but then was lost in the lineage of cynodonts that evolved into mammals. So during the Triassic, somewhere between 244 million years ago. So we even know, we kind of know quite well when that event happened. And one of the prerequisites for that was likely endothermy, like warm-bloodedness. So if you are warm-blooded, you don't need a special organ to tell you when you're gonna bask. And against that, we have some coprolites. So coprolites are fossilized poop. And these coprolites indicates that there may have been hairs as early as the Permian. So absolutely contradictory evidence. So as I said, this was very well summarized in the last 2 weeks, because in the last 2 weeks we had a paper coming out saying everybody is warm-blooded, and another paper coming saying nobody was warm-blooded. So yeah, it's a matter of debate. But the team here in South Africa, the team that I work with, we've made some progress with most notably with the evolution of hair.
Right. What about fur and hair? If mammals descended from reptiles, how did hair evolve?
Yeah, that's the very big question. So hair would be the ultimate and maybe the only strong evidence for the evolution of warm-bloodedness. You need hair to keep your body warm, to act as a fur coat, a natural fur coat that keeps your body warm, like an insulation layer that keeps your body warm. So now the big question is, when did those hair evolve? And unlike dinosaurs, in which we have all those beautiful Chinese fossils that document the transition almost perfectly from scales to feathers and flight-capable feathers, in synapsid evolution, we don't have that fossil record. We don't have that beautiful transition from scales to hairs. So we know we started from scales, from fossils. As I say, we have Varanopids from Germany. We have Archaeotheris from North America. We have scales impression from Poland that definitely demonstrate pelycosaurs, so the first step in the synapsid evolution, that they did have scales. So that's reptilian-like scales. And we know from the study of modern species, embryological studies, that hairs are basically transformed scales. So I know most textbooks, old textbooks, say the opposite, that hairs are not transformed scales, but this has changed recently. In the last 10 years, new evidence have come to show that scales in reptiles and hairs in mammals are both the structures are derived from an embryological epidermal common ancestor in the embryo called a placode. So the epidermal placode turns into a scale in reptiles and turns into a hair in mammals. So there is a common embryological lineage. So we can safely assume, because of that the scales of our pelycosaurs likely evolved into hairs. The problem is the fossil record gives us a very mixed signal, because so pelycosaurs have scales, but then you look at your therapsids and your cynodonts, and we don't find any evidence of scales in those guys. We have skin impressions of, well, likely skin impression, may I say. It's not even sure they are actual skin impression. They are still not studied, but they have been reported in published literature. So I authorize myself to talk about them now. They do exist in the literature. So there are skin impressions of therapsids, the Dinocephalian Estemenosuchus from Russia, Lystrosaurus from South Africa, Moscorhinus also from South Africa. They all have skin impressions, and these skin impressions are absolutely barren, naked. There's no scale and there's no hair on them. It's just, well, just like a human skin. There's nothing. We don't even see hair follicles. On Estemenosuchus, there may be some glands, but we don't see much. There's no tegument. That's what we call them. So there's no tegument on them. So it's very puzzling. And then, as I said, there's no skin impression at all for cynodonts. And then you get to mammals, and in mammals we have hair. So then we get the point where we get those Chinese fossils, those Mesozoic Chinese fossils with the beautiful preservation that document the evolution of feathers. From the same sites, the same deposits, we have also mammals, and these mammals have hairs, but they are already mammals. So it's not a big surprise. Mammals with hairs, that's not unexpected. So now comes the big question: when did hair evolve? Those reports of naked skin, are they actual naked skin? Are these actual naked skin? Or is this because of decay that the hairs or the scales were lost, like they just shed from the skin, leaving just a barren impression on the rock? That's the big question at the moment. And so, as I said in the previous question, we made significant progress in that transition from scales to hair by studying the nerves that innervate, that give impulse and get information, nervous data from the hairs. So these nerves, that's the nerves of the face that in modern mammals innervates the whiskers. So it's called the trigeminal nerve. It runs approximately here in your cheeks. We don't have whiskers anymore, but I mean the area of whiskers is more or less here. So facial whiskers are present in most mammals, and primitively, at least we know ancestrally, mammals were whisking, which is moving their hairs to sense their environments, and most mammals still do that, except primates. Of course, primates have to be exceptional. But yeah, this trigeminal nerve leaves distinct imprints in the bone that can be followed across pelycosaur, therapsid, cynodont, and mammalian evolution. And we can see, in fact, that in the early pelycosaurs, the imprint on the bone, inside the bone actually, was very complex, which means that the whole nerve was completely encased in the bone. And that completely prevents whisking. If you try to whisk with your bones, imagine a pelycosaur like Dimetrodon had whiskers. He could not whisk because the nerve was completely stuck in the maxilla, in the bone, and so the nerve cannot move and follow the movements of the whiskers during the whisking movements. And we also know it doesn't have the muscles also to whisk at all, because there's no muscle scars on the skull. And when you move towards the mammalian condition, so once again I can illustrate the mammalian condition here. So the mammalian condition, which you can see here quite clearly, you see that hole. This hole is called the infraorbital foramen. All mammals that live today have an infraorbital foramen, and it's just one big hole under the eye socket. And this one big hole gives passage to the whole nerve, and the nerve then ramifies in the cheek and in the lips, and is free to move with your cheeks and your lips. So it's no longer encased in the bone. So we worked on the hypothesis that the transition from a reptilian-like, completely encased trigeminal nerve into a free-to-move nerve passing through an infraorbital foramen only would mark the transition from no whiskers to whiskers. So if you follow that hypothesis, then you look at the fossil record and you try to look for the first infraorbital foramen, basically. And the earliest evidence of an infraorbital foramen, and that's where it gets interesting, is as old as the loss of the pineal foramen. So as the cynodonts were transitioning into whiskers, into whisking, as they were acquiring an infraorbital foramen that enabled them to whisk, they were also losing the pineal foramen, which, as we said earlier, is an indicator of a transition from cold-bloodedness to warm-bloodedness. So, and that coincidence is very, very intriguing. So we kept investigating on that, and now there will be very soon published new evidence that actually warm-bloodedness may have evolved once again some 244 million years ago in cynodonts. This is still unpublished, so I cannot disclose that now. But very soon there will be more evidence that the transition from cold-bloodedness to warm-bloodedness and the origin of hair associated with that probably evolved 240 million years ago. And this is very important because hair is not only the evolution of endothermy, it's also linked to the evolution of lactation and milk.
Well, another aspect of being a mammal is mammary glands and the production of milk to feed the young. So how did this come about?
The evolution of the ability to milk the young, so give milk to the young, lactation, is also one of those big transitions that we think happen between the origin of synapsids and the onset of mammals. So somewhere in between those four stages, they started giving milk to their young. We know that this transition happened because so far no one, unlike the endothermy story, so far no one has hypothesized that everyone was producing milk at the very origin of amniote. So we are quite confident this time that this transition happened on the synapsid line. And of course, we have monotremes today that produce milk. So all mammals, even the most, even the ones with the most, and I will use the word primitive. So even the one with the most primitive biology also give milk to their young. So now the big question is, when did that happen and how did that happen? So from the study of monotremes, we know that monotremes, as I said, don't have nipples. So they don't have that particular area of their body that is more sensitive and that specifically exists to excrete milk. So they just have a broad patch on their belly where the skin is capable of producing milk, but it's just a general patch on the belly. So the baby monotremes are just lying there on the belly and they are sucking on dreadlocks of milks, basically. So the hairs are just packed by the milk and they are sucking on that. So besides the disgusting side of that story, this is very interesting because it tells us also that the hairs play an important story in the origin of lactation. And in fact, when you look at the histology of a mammary gland, you realize that all mammary glands are tightly associated with hairs. So in a monotreme, for example, all those tiny mammary glands are associated with a bristle. And when you look at marsupials in the marsupial pouch, even marsupials, the mammary glands and the nipples are also associated with hairs. It's only in placentals that we don't have hairs associated with our mammary glands. But in general, all of our mammals, besides placentals, have their mammary glands tightly associated with hairs. And this comes from a very weird story, is that mammary glands are actually modified sweat glands. When you look at the proteins that are produced by the mammary glands, they are just modified versions of the same proteins that are produced by your apocrine glands, which are your sweat glands. So it's just a modified version of sweat. Milk is just a modified super fat, particularly the fat.
Are we talking about the sebaceous glands as well?
So the sebaceous gland played a minor role. It's mostly the apocrine. Glands.
Oh, okay.
But the sebaceous gland also produce some stuff that you find in the milk, but in a lesser proportion. And there's a little bit of the proteins that you find in blood also. So it's like the whole body at that particular level came together to produce milk, with a major contribution from the apocrine glands, and then minor contributions from here and there. And you see all that in the chemistry of the milk, of modern milk today. So and this is very consistent with the fact that just like all the sweat glands, all the mammary glands are also associated with hairs. So that's a very consistent story that tells us exactly where does milk come from. And now, when did the mammary glands originated? That's a super, super big question. That's still a question mark, but again, our story with the pineal foramen will be of interest here, because what you see in modern mouse is that when you manipulate genetically modern mouse, and particularly when you knock off a gene called MSX2, when you knock off that gene, you create mouse that have a pineal foramen, have no hair, and have no mammary glands. So you turn them into a cynodont or a therapsid. You basically transform your mouse with just one gene knocked off. You turn your mouse into the basic body plan of a therapsid. And that's very interesting because there's the hair which are lost. There's the mammary glands which are lost. So again, you find that association between hairs and mammary glands. And there's the pineal foramen that comes back. And that pineal foramen is an osseous feature that we can very easily follow the evolution across the geological time, across the fossil record. And as I told you, pelycosaurs have a pineal foramen, therapsids have a pineal foramen, mammals don't. And the transition from pineal foramen to no pineal foramen happens in cynodonts 240-ish million years ago. So if the genetics of our cynodonts worked the same way as the genetics of mammals does today, well, mouse in this particular case, mice, because we haven't done that gene manipulation on any other mammal besides mice. But if it works the same way as in modern mice, then the disappearance of the pineal foramen might mean that there was a mutation of MSX2 in cynodonts that led to the origin of hairs and mammary glands. And that's that's quite an amazing perspective. Unfortunately, we are lacking, as I said, the skin impressions to support it. But if that that Evo Devo, it's an Evo Devo story. If that Evo Devo story is true, then we could pinpoint the exact moment when the mammary glands originated from the first time, about 240 million years ago. And there is another element to that story that we must mention at this level. It's the secondary palate. So all mammals, so if you look at my mammalian skull here, all mammals have what is called a secondary palate, which is an osseous separation, a bony separation between the nasal cavity here and the mouth. Reptiles don't have that osseous separation. And this secondary palate is important because it enables the creating the pump with the tongue. So with your tongue, you can create a pump because you pump against that secondary palate. And that pump is an important device to suck on milk or on dreadlocks if you're a monotrim. And and what's interesting is that when the pineal foramen was lost, and so when the possible lactation appeared for the first time, the secondary palate was already there. So everything that a mammal needs to pump that milk was in place a little before the mammary glands actually evolved.
Well, I guess the question that we're left with is, why did this occur?
So why is a big philosophical question. How did that happen? We have actually there's a lot of course debate on the reasons, the big evolutionary reasons, how and why this would have happened. I think we should start first with what I think and what everybody thinks is probably what was the biggest, most important biological event since the very origin of life. And it's that time when life almost went completely extinct. And it's the Permian Triassic extinction. So pelycosaurs originated in the Carboniferous and carried on in the early Permian. In the early Permian, there was a first crisis, a biological crisis, extinction, called the Guadalupian crisis, which marked the transition from pelycosaurs into the therapsids and the cynodonts. So therapsids and cynodonts take over the pelycosaurs after the end Guadalupian extinction. Although there was already the signs of that transitions already in the middle Permian, but let's make it simple. So there's a first crisis that strike synapsids before the end of the Permian, but when we reach 252 million years ago, then happens the Permian Triassic transition, which is characterized by the extinction of an estimated 90% of everything that lived at the time. So 90% of everything that lived suddenly, more suddenly in the geological time, dies off. Here in South Africa, we have evidence that this extinction took 4 steps, and in 4 steps you go, and it's very conspicuous when you go in the field and you see those fossils. You see how the certain species go extinct. You see how certain species go from a skull that size into a skull that size, the Lystrosaurus in particular. So you see how all those species, some of them cope and most of them die during that transition, and how they are replaced afterwards. So for example, the big carnivores, the Gorgonopsians, become completely extinct and are replaced by the archosaurs, so the ancestors of dinosaurs. you see how the paleosaurs, those big fat reptiles like a Scutosaurus, become extinct to be replaced by new herbivores, and particularly Lystrosaurus, and then you will have all those archosaurian herbivores like the Aetosaurs, for example. In the seas, you have the origin of ichthyosaurs, for example, and many other sea animals. And the sharks, well, the ancestors of sharks, the cartilaginous fish, also take a huge toll at the end of the Permian. So you have that event that has basically changed life forever. And from that point, that's where you see the cynodont rise. The cynodonts begin rising. They were very almost anecdotal before the extinction, and after the extinction you see them diversifying, taking over many ecological niche. And in parallel, you see also the archosaurs are taking over a huge part of the ecological niches. And there is kind of a fight between them. Of course, it's just they are just challenging each other on the ecosystems. They are not actually having a war, of course, but yeah, you see those two families diversifying in the Triassic in the aftermath of the extinction, and basically the archosaurs win, and the archosaurs take over, and by the mid-Triassic, you see the diversity of cynodonts decreasing, to the point that at the end of the Triassic, there's a new mass extinction. So just 10 million years after the Permian Triassic mass extinction, there's a new mass extinction. And there's nothing left of the cynodonts after that, except one lineage of tiny animals that will ultimately become the mammals. So, and all that story that I told you, the transition with the jaw articulation, the transition from scales to hair, all of that happened during that mass diversification of cynodonts in the Triassic. And only the lineage that has accumulated those tiny bits of mammalness survived. Hadn't it survived, I don't know what mammals would look like. Or if we would call them mammal. Would we call ourselves mammals? I don't know. But it's the one that survived, and that's so. And they probably, and now we are thinking a posteriori. So we are thinking about the war after the war happened. So of course there was only one outcome that we can discuss about. So of course it's very biased, but that's the best we have, unfortunately. So thinking after that, we look back at this lineage of cynodonts, and we see that this particular lineage of cynodonts that evolved into mammals and that survived became very small. That's the one that became very small. That's the one that probably evolved warm-bloodedness. That's the one that likely evolved lactation and parental care that goes with it, and that's the one that became nocturnal. And all of this combined, we think we can hypothesize that all of this combined give them an advantage against the rising archosaurs, and by the Jurassic we can say against the dinosaurs, give them an advantage because they could actually carry on surviving despite the dinosaurs. So living in the shade, that's usually what we say about those Mesozoic mammals. They survived in the shade of dinosaurs. So in the early Jurassic, that was as close as you can get to the truth, like really just a world dominated by archosaurs in the aftermath of the third mass extinction in just a very short time. They went from the dominant animals into tiny nocturnal animals, warm-blooded, that that managed to survive to those dominant archosaurs because they lived in the night and they were small, very inconspicuous. They could avoid predators very easily. They were trying to avoid competition at all costs, hence the small size. When you're very small, you need less resources, so you don't compete for resources. Insects were the fuel of mammalian evolution at that time. We often forget about our invertebrates mates, but insectivory was really the fuel of that transition from cynodonts to mammals and the survival of mammals across the Mesozoic. It's only later, in the late Jurassic and particularly in the early Cretaceous, that mammals will rediversify. Well, you will start seeing herbivorous mammals again, big body-sized mammals, well, big, never bigger than 10 kilograms, but, Repenomamus and Adalaterium reached the 10 kilogram threshold, which is relatively big for a Mesozoic mammal, even though it's quite puny compared to the biggest dinosaurs. So yeah, and only later in the Jurassic and particularly in the Cretaceous, mammals will come back again, and synapsids in general, because mammals are the only representative left of that synapsid lineage that used to rule the world in the Permian and early Triassic, and now is reduced to those tiny guys. So all modern mammals living today are descended from that shrew-like, from those tiny shrew-like animals, no bigger than this, plus the tail, but no bigger than this, and that survived in the shadow of dinosaurs. And today we still see the signs of this in the biology of modern mammals, because a lot of our biology today is directly inherited from the biology of these nocturnal mammals. So you've probably heard that most mammals are colorblind, for example. And it's because all mammals are descended from an animal that was nocturnal, so had absolutely no advantage at seeing color, so became colorblind. So the eyes, they have a bichromatic vision, and we primate re-evolved a trichromatic vision from that bichromatic condition. So we primates are the only exception in a world of colorblind mammals today. Some marsupials are not colorblind also, but us among placental mammals are one of the few exceptions. So that's directly inherited from our nocturnal ancestor. The fact that we have a coiled cochlea in our inner ear, that coiled cochlea is an adaptation to hear a wider frequency of sounds, and that's to compensate for the loss of color vision. Because vision became a less important sense organ, it was compensated by the evolution of better hearing. The evolution of the ossicular chain is also associated to that. So the evolution of the ossicular chain is also improves the sense of hearing in mammals, the acuity and the range of audible frequencies, and whiskers. All mammals today have whiskers, except primates once again, but all mammals again have whiskers and have a very sensitive face in general. And that's again directly derived from our nocturnal ancestors that had to rely on whisking to orientate themselves in the dark. So most of and today even non-nocturnal mammals, diurnal mammals, still retain whiskers, and some mammals have even lost the ability to whisk, like primates, for example. But the nerves and all that sensitivity, that facial sensitivity, is directly co-opted from that nocturnal condition. So we have more And in fact, some paleoneurologists, so paleontologists specialized in the evolution of the brain, think that it's because of all that new sensory inputs that evolved into our nocturnal ancestor to compensate for the loss of sight. It's because of all that sensory inputs that our brain became significantly bigger than those of reptiles, or at least reptiles of the same size, of course.
Well, this is definitely one of the most fascinating subjects I've covered on this channel, and perhaps we can have you back one day to go into even more detail about synapsids and the origin of mammals. So what about any upcoming projects? Is there anything exciting you have in the works that you can tell us about?
Yes, well, that was a pleasure for me too to join us on your channel. Yes, well, as I say, we have upcoming stuffs on the evolution of warm-bloodedness that are going to come out very soon, I hope. So well, another brick into the ever-growing and extremely contradictory wall of the evolution of warm-bloodedness in mammals. But yeah, and now that I have a permanent position, what I'm trying to build here is really field work. So not just documenting the things with a CT scanner as I've been doing so far. I use X-ray to document the evolution of all those things that I talked about today. But it's also bringing new fossils into the mix. Because we have been doing fieldwork recently and find a lot of exciting stuff. So I know one of the questions that people ask a lot is, haven't we find everything already? And the answer is, well, no. My God, no. We are still finding new exciting things. Well, that one, I already wrote something about it, so I can talk about it. But for example, the gorgonopsians, so the big saber-toothed animals that were the dominant predators in the Permian. These gorgonopsians, we thought they evolved from small animals and then grow into super carnivores. And actually what we discovered is that the earliest gorgonopsians were probably as big as the latest ones. So we have now occurrences of super large, super old gorgonopsians, which questions basically everything that we thought we knew about gorgonopsians so far. So that's one of the things that's coming also. So yeah, and new stuffs can only be found in the field. So I'm really working at increasing our input of new fossils and new species in the future.
I will leave links to your research papers and social media in the description below, and all that's left to say is thank you very much indeed, Julien, for coming on to Evolution Soup.
Thank you very much for giving me the opportunity for giving my French accent the opportunity to express itself. This was a great pleasure. Thanks.